All right, we're back. What we'd like to deal with now is Newton's laws as applied to circular motion. And there's a couple of common misperceptions and mistakes that we want to avoid in this situation. To start off with, how would you apply Newton's second law? We've got the net force centripetal equals the object's mass times its centripetal acceleration. Now notice again, it's the same thing. It's just applying Newton's second law, subscript C and C. As we learned in the last chapter, if an object's going around a circle, it is accelerating. So there must be a net force towards the center when you see that. Let's, for example, take a situation of a vertical circle, an object spinning around on a rope or something in a vertical circle. So here's our circle right here. And let's look at this object in a couple different positions. So let's look at the object when it's right here. We'll call that position 1. We'll look at the object when it's right here. We'll call that position 2. We'll look at the object when it's right here. We'll call that position 3. And finally, last but not least, how about when it's right over here? Okay, we'll see what happens there. We'll call that position 4. And we want to write an equation of motion. When they ask you for an equation of motion, they mean what's the Newton's second law equation for the most part. So what's the Newton's second law equation for each of these positions? So let's take a look at, in the first situation right here, what are the forces acting? I'm going to draw the free body diagrams right in this diagram. So let's say that it's going around in a circle because it's connected by a rope. I'm going to put the rope in like a light blue color here. There's our rope right there. Over here, the rope is pulling it that way. Over here, the rope's pulling it that way. And here, our rope is like that. Okay, so at this position right here, we've got a couple different forces. We've got our force of gravity pulling down. I'm going to call that mg. But we also have the tension of the rope pulling down like that. T. So for situation number 1, our equation of motion, by the way, on these, you always want to make this, the centripetal acceleration, positive. In other words, toward the center of the circle should be positive for all these problems. No matter where you're analyzing it, you always want to make positive towards the center of the circle, and that'll make this always work. So for position 1, mg, is that towards the center of the circle? Yes, so that's going to be positive. And all I'm doing is I'm taking this equation, I'm getting specific for each of these positions. So mg is positive, and so is t. Plus t is positive. That will equal m times ac. Now notice that the centripetal force, let's say I drew something like this. I drew that and I labeled it FC. What is wrong with that? It's totally wrong. There is no separate force that's the centripetal force. Never, ever will you put something labeled centripetal force on a free body diagram. The question is always, what is providing the centripetal force? In this situation, the force of gravity and the tension force are both combining to provide the net centripetal force. And that net centripetal force always has to equal this. So that's position 1 right there. Let's go to position 2. For position 2, the only force that is acting on it, now gravity, of course, here's my free body diagram. We've got mg going down this way. That may cause a tangential acceleration, but it won't cause a centripetal acceleration. This force right there, tension, this is the only force towards the center. So this may speed it up at that point, but it won't keep it going in a circle. So in this situation, all it is, and the only one that there is the tension will equal MAC. That's the only force pointing centripetally. Let's take a look at situation 3 right here. In position 3, we've got, let's draw each of our individual forces in our free body diagram. We've got this force. That is the tension. But our force of gravity in this case is pulling down that way, mg. Now that's not, let's get it to scale. If it's going in a circle, this mg has got to be smaller than our tension force. Otherwise, it won't stay going in a circle. The net force won't be towards the center. So this is our tension. This is our tension. This is mg. Tension's got to be greater than mg to keep it accelerating towards the center. So for this situation right here, always make towards the center positive. That means we've got t here, positive, but it'll be minus mg because mg is pointing away from the center. Again, the trick is always make towards the center positive. For our final situation right here, we're going to have to draw a brand new diagram. So we're going to redraw this whole situation for our one problem where we've got an object that is, here's the center of a circle, it's over here at some angle, and I made that, that color was blue. So we'll make this blue. Here's our object right here. And we're going to say that this is at an angle with the vertical that is angle theta. That's theta with the vertical. So we got to draw all of our forces, and we've got to, again, divide this up into components. So let's go ahead and just draw the forces on here. mg is pointed straight down. But we need positive to be, and there's a tension right here. We need our positive direction to be towards the center of the circle. So we have to break up the force of gravity into components, one of which is along the radial direction. That's one component of gravity. And the other component of gravity has got to be a tangential component. Notice I'm dividing it up into radial right here and tangential right here. So these are not separate forces. These are just breaking up the force of gravity into its components. So let's go ahead and figure out what angle is what. Notice that this, and this is how we always do this, notice that this side is parallel to this side, and, go to green, this side is parallel to this side. So where is this angle theta? You might have thought it's down here. It's not. Red, green, the angle theta is right up here. There's theta. Cool, we got that. Now let's figure out our components. Again, the force of gravity is the hypotenuse. So this side is the opposite. This will be, this is mg sine theta. This side over here is going to be mg cosine theta because it's the adjacent side to theta. So when we write our Newton's second law equation, again the general equation, net force C equals MAC, our radial forces are T, and ask yourself, is that going to be positive or negative? Well, tension is towards the center, positive, T, and then this force is going to be negative because it's away from the center. But what is that force? It's mg cosine theta. And that, in this case, will equal MAC.